Good day, everyone. My name is Shaymel Agat, and today I am going to talk about venturimeters. Okay, for the overview of the study, this study is about the venturimeter and its application in measuring fluid flow inside pipes. A venturimeter works based on the principle that when fluid passes through a small surface section of a pipe, its velocity increases while its pressure decreases. So, by measuring this pressure difference, the flow rate of the fluid can be calculated accurately. So the device consists of three main sections: the converging section, the throat, and the diverging section. So in the converging section, the fluid accelerates as the pipe diameter decreases. At the throat section, the velocity reaches its maximum while the pressures becomes slowest. In the diverging section, the pipe gradually expands, allowing the fluid to slow down and recover part of its pressure. This experiment uses the Bernoulli equation and continuity equation to analyze the relationship between pressure difference, velocity, and discharge. So the venturimeter is widely used because it provides accurate measurement with minimal energy head loss, making it important in hydraulic system, water distribution, and environmental engineering application. Next slide. The theory. So, the operation of a venturimeter is based on the Venturi effect. This principle explains that when a fluid flows through a narrower section of a pipe, its velocity increases while its pressure decreases. According to the continuity equation, the flow rate inside the pipe must remain constant, so reducing the cross-sectional area forces the fluid to move faster. At the same time, Bernoulli principle states that the total mechanical energy of the fluid remains constant. Because of this, an increase in velocity results in decrease in static pressure. This pressure difference between the inlet section and the throat is what allows the flow rate to be measured. So to derive the discharge equation of the venturimeter, the continuity equation and Bernoulli equations are combined. The continuity equation relates the velocity and area at the inlet and throat section, while Bernoulli equation relates the pressure and velocity changes between 2 points. By combining this relationship, the pressure difference can be directly connected to discharge or flow rate of the fluid. So for this experiment, a virtual fluid flow system was used to simulate the operation of a venturimeter under real pipe conditions. So the setup included horizontal pipes with different diameters fitted with the venturi tubes to observe changes in fluid flow and pressure. A digital differential U-tube manometer was used to measure the pressure difference between the inlet and throat section of the venturimeter. Flow regulating valves control the movement and flow rate of water inside the system. So a collecting tank with a piezometer scale was also used to collect discharged water and monitor the rise in water, which was necessary for calculating the discharge rate and coefficient of discharge of the venturimeter. So for the method, the experiment began by selecting a pipe which is 20 millimeters from the virtual system while keeping all other valves closed. The main inlet valve was then opened to allow water to flow through the venturimeter section. So before taking measurements, the manometer was vented to remove trapped air and ensure accurate pressure reading. Once were achieved, the pressure difference between inlet and throat section was recorded using differential manometer readings. To determine the actual discharge, the outlet valve of the collecting tanks was closed and the time required for the water level to rise by 5 centimeters was measured using the digital timer. The collected data were then used to calculate the actual discharge, theoretical discharge, and the coefficient of discharge of the venturimeter. For our results and discussion, Table 1 presents the geometric constant and system constraint using the venturimeter simulation. As you can see, we can see here the inlet diameter, which is 2 cm, the throat diameter, which is 1.36 cm, area of inlet, which is 3.49 centimeters squared, area of throat, which is 1.45 centimeters squared, area of the collecting tank, which is 6,750 centimeters squared, rise of water level is 5 centimeter, and the acceleration due to the gravity is 981 centimeter per second squared. So, by keeping these geometric properties fixed, any change observed in the discharge measurements were mainly caused by variation in fluid velocity and flow conditions rather than a change in the apparatus itself. This helped ensure consistent accuracy and reliability in the experiment results and calculation. Table 2 presents the manometer observation and measured head loss obtained from the 4 experimental trials in the venturimeter setup. So, the left limb and right limb readings varied across the trials, showing changes in pressure distribution between the inlet and throat section of the venturimeter under different flow conditions. The left limb reading ranged from 42 centimeters in trial 2 to 58 centimeters in trial 4, while the right limb reading ranged from 15 centimeters to 40 centimeters. These differences in manometer readings directly affected the calculated head loss values. The lowest head loss was recorded in trial 2, which is 25.20 centimeters, while the highest was observed in trial 4, which is 541.80 centimeters. Trial 1 and 3 also showed relatively high head loss value, indicating stronger pressure differences during those runs. These collection times also varied significantly. Trial 2 recorded the longest collection time of 95 seconds, which indicates a lower flow rate. In contrast, Trial 4 recorded the shortest collection time, which is 21 seconds, corresponding to a much higher flow rate and discharge condition. Proceed, Table 3 presents the calculated value of actual discharge, theoretical discharge, and coefficient of discharge for the 4 experimental trials. The actual discharge values range from 355.26 centimeters per second to 1,607.14 cubic centimeters per second, while the theoretical discharge values were slightly higher in all trials. The coefficient of discharge, or CD, represents the ratio between the actual and theoretical discharge. The calculated CD values range from 0.85 to 0.98, indicating that the venturimeter operates with relatively high efficiency throughout the experiment. Among the trials, Trial 2 produced a highest coefficient of discharge at 0.98, which suggests that the system experienced very small energy losses under those flow conditions. On the other hand, Trial 1 had the lowest coefficient of discharge at 0.85, indicating relatively higher losses caused by friction or turbulence within the system. So for this figure, the analysis of flow characteristic, it illustrates the characteristic curve of the venturimeter by plotting the actual discharge against the measured head loss. So the graph does not show a linear relationship. Instead, it follows a non-linear pattern that agrees with the theoretical behavior of a venturimeter. So the result demonstrates that the discharge is proportional to the square root of the head difference, expressed as Q proportional to the square root of H. This means that as the flow rate increases, a much larger pressure differences is required to produce that increase in discharge. The graph also shows the higher volumetric flow rate requires progressively great pressure drops. Fluid pass through the restricted throat section of the venturimeter. Overall, the result confirmed expected relationship between the discharge and pressure head difference based on the principle of fluid mechanics and venturimeter operation. So in conclusion, the venturimeter experiment successfully achieved its objectives of determining the coefficient of discharge and analyzing the relationship between volumetric flow rate and pressure head loss in the system. The experimental data showed that as the pressure head loss increased from 25.20 centimeters to 541.80 centimeters, the actual discharge also increased from 355.26 cubic centimeter per second to 1,607.14 cubic centimeter per second. So this clearly demonstrates a nonlinear relationship between discharge and head loss, which is consistent with Bernoulli's principle where flow rate is proportional to the square root of the pressure difference. The average coefficient of discharge obtained from the four trials was approximately 0.925, indicating that the venturimeter operated with high efficiency and the actual discharge values were close to the theoretical predictions. However, since the coefficient is slightly less than 1, it also indicates that the presence of minor energy losses in the system. So these losses can be attributed to friction, turbulence, and shear stresses as the fluid passes through the converging and diverging section of the venturimeter, especially at a higher flow rate. Y'all, I hope you learned something. Thank you and have a good day. Bye bye.